Okay, so we're just going to finish up lesson 104 and then do 107. And just remember that a geometric series is a series where you have some term you start with, a sub 1, and then for each term that comes after that, you multiply by the common ratio r to get your next term. So you would have something like maybe if your first term is 2 and your common ratio is 3, you would have something like 2, 6, 18, 54, and so on. So that's a geometric series. That's a geometric sequence, and a geometric series is when you add the terms of a sequence. So just reminding you about that. All right, so we just had a couple more problems to go over. Geometric series whose first term is -8 and whose common ratio is -2, and we want to find the sum of the first 9 terms. So s sub 9 is going to equal a sub 1, so that's -8, times 1 minus r, which is -2, to the n, which is 9, and then that's all going to be over 1 minus r, which is -2. All right, so when we add this up, we've got 1 minus -2 to the 9th power. So -2 to the 9th power, it's raised to an odd power. We've got a negative number raised to an odd power, and so that is going to be negative. And it's -512. So -512, and then that's all over 1 minus -2, which is 3. So you've got -8 times 1 plus 512, which is 513, over 3. And if you punch that into your calculator, you get -1,368. Okay, now the next example may seem like, why would we just add, one more term? But it completely changes the sum, because when you raise a negative number to an even power, like 10, you're going to get a positive number. So to find the sum of the first 10 terms of this sequence, we are going to do s sub 10. A sub 1 is still -8. And then we have 1 minus -2 to the 10th power, all over 1 minus r, which is still 3. So -2 to the 10th power is positive 1,024. So you've got -8 times 1 minus 1,024 over 3, and that's going to be -8 times -1,023 over 3. So this time you're going to get a positive number. So that 10th term is so big that it outweighs all the other terms, and you end up with a positive sum. Because, when you added the first 9 terms, you ended up with a negative number. You add one more term, and you end up with a positive number. That's pretty big. It's 2,728. So you can see that as you are adding higher and higher powers of -2, it's getting bigger and bigger, and each term is getting exponentially bigger. So the sum is getting large positively, and then again, when you move on to the 11th term and add that, you're going to end up negative again. So, but the terms are getting bigger and bigger, more and more. Absolute value is getting bigger and bigger, because 2, or -2, is a number greater than 1. Now we're going to start talking about convergent geometric series, and this is a situation where your terms are getting smaller and smaller, because we're going to be dealing with series that have a common ratio between -1 and 1. Things that have a common ratio whose absolute value is less than 1. Things like 1/2, 1/3, 2/3, fractions like that, that when you raise that kind of fraction to a power, it doesn't get bigger, it gets smaller. So again, just reminding you about the formula we derived, and there it is. So suppose we have a geometric series, like I just said, where r is a number between -1 and 1. That is, the absolute value of r is less than 1. In this case, when n is very large, r to the n gets very small. For example, think of 1/3 to the 10th power. It gets very small, 0.000016935. So when you raise a fraction less than 1 or greater than -1 to a power, it doesn't get bigger, it gets smaller. So this is the thing you have to keep in mind when we're talking about this. The higher power you raise it to, the tinier it gets. So since r to the n is getting very small when you have an r like that, the term here, 1 minus r to the n, which is up here in our formula, begins to approach 1, because when n gets very large, that r to the n is so tiny that it doesn't really even affect the 1. And so that part of the formula, when n is very large, gets close to 1. So the whole numerator of this fraction will start getting closer and closer to a sub 1 times 1, which is just a sub 1. So just to kind of wrap your head around what I'm saying, this part of the formula, if you had an r something like 1/3, 1 minus 1/3 to the 10th is 1 minus that tiny amount we were just talking about, which is basically 1. I mean, it's still just almost 1. So you can imagine if n gets really huge, bigger than 10, if it gets to be 1,000, then that r to the n is just, it doesn't really even affect the 1 at all. So the bottom line is that if you have a sequence where your ratio, your common ratio, is less than 1, greater than -1, absolute value less than 1, then this formula really becomes s sub n is equal to a sub 1 over 1 minus r, because that 1 minus r to the n is approaching 1. A sub 1 times 1 is just a sub 1. Okay, so this leads us to something that seems very strange when you first start encountering it, but this is something that you will deal with in calculus constantly, because this is kind of what calculus, the basis of everything you're going to learn in calculus, is that it is possible to add an infinite number of things and get an exact value for the answer. So there are 2 videos here that help you grasp this idea, that help you wrap your head around it. But it is, at first, when you first encounter this, it seems almost like magic, like it's not really possible to do. So in calculus, we use the word limit to talk about when I say that something approaches a number. So when I say that 1 minus r to the n approaches 1 as r to the n gets smaller, so in calculus, you would write it this way. You would say, if the absolute value of r is less than 1, then the limit as n approaches infinity of 1 minus r to the n is 1. So it's this idea that as n gets very large, approaching infinity, we say, that r to the n shrinks, because if r is less, the absolute value of r is less than 1, then this gets so tiny it becomes negligible, and you approach the number 1. So if we have an infinite series with a common ratio between 1 and -1, we can actually find the exact sum of that series. This type of series is called a convergent series because its sum converges on a specific number, that is a sub 1 over 1 minus r. This is what we're talking about in this lesson. We're talking about convergent geometric series. We're not talking about all geometric series. We're just talking about convergent series. Convergent series are geometric series whose common ratio is less than 1, greater than -1. If r, however, and we've looked at many series like this already, if the absolute value of r is greater than or equal to 1, the series is divergent, and you can't find the sum. You can only find the sum of the first n terms, which is what we've been doing, but you can't find the sum of all the terms. And so this is just a very special kind of series we're talking about now. So if we have a series like this, and we want to find the sum of this series, all the terms to infinity, then we will use the formula we just talked about, a sub 1 over 1 minus r, because the 1 minus r to the n part of the formula goes away. Well, it doesn't go away, it becomes 1, and a sub 1 times 1 is just a sub 1. So that's where that comes from. All right, so this geometric series, the first term is 5, and the common ratio is 1/2. You can see that you're multiplying by 1/2 every time. 5 times 1/2 is 5/2. 5/2 times 1/2 is 5/4. 5/4 times 1/2 is 5/8. And if you're dealing with, remember, if you're dealing with any geometric series, you can just divide a term by the term before it to find out what r is. So 5/2 divided by 5 is r, so that's 1/2. All right, so we know r is 1, we know our r, and so we can find the sum of this geometric series, and that is 5, is 1, over 1 minus 1/2, and that is equal to 5 over 1/2, which is equal to 10. Believe it or not, if you add this up, it will approach the sum. If you keep adding more and more terms, you can add more and more and more terms, and this sum will approach the number 10. And it won't ever get there, and it won't ever go over 10. So that's what we say it converges on. The sum of this series converges on 10. All right, I'm going to erase this so that you can see, get an idea of that this is really truly happening. So let's look at some terms. 5 plus 5/2, so that's the first two terms, adds up to 7.5. The first three terms add up to 8.75. The first four terms add up to 9.375. Then the first 5 terms add up to 9.6875. The first 6 terms add up to 9.84375. The first 7 terms add up to that. The first 8 terms add up to 9.9609375. The first 9 terms add up to 9.98046875. And then the first 10 terms add up to this. First 11 terms add up to this. First 12 terms add up to that. And as you keep going, it just keeps getting closer and closer to 10. It never actually gets there. If you add 1,000 terms of this geometric series, it will not reach 10. It will just get closer and closer and closer. And that's what we mean when we say the sum of this infinite geometric series, this convergent series, converges on 10. All right, so a ball is dropped from a height of 12 feet and rebounds 2/5 of the fall distance on each succeeding bounce. How far will the ball fall on the 10th fall? And what will be the total distance the ball has traveled? Okay, so let's just see what's happening here. You're dropping a ball. It goes down, up, down, up, down, up, down, up, down, up, down, up, and less each time. And at some point, if you're in a vacuum, it will keep bouncing forever. But of course, in the real world, it will stop because things will act against it to keep it from going. So the first time you drop it, it falls 12 feet. And then it rebounds 2/5 of that, or 4/10 of that. So the common ratio for what is now a geometric series we're talking about is 0.4, or 2/5. And so each time the ball falls, it bounces back up 2/5 of the amount it bounced up before. So we want to know how far will the ball fall on the 10th fall. And so that's what we have right here. 12 times 0.4 to the 9th, 10 minus 1. So a sub n, a sub 10 is equal to the first fall, 12 times 2/5 to the n minus 1, which is 9, which is what I wrote down there. Anyway, so if you punch that into your calculator, you're going to get 0.00315452. So for part B, what will be the total distance the ball, and this is really supposed to say, will travel? For that, we're talking about an infinite geometric series, a convergent infinite geometric series, because we have this r that's 2/5, which has an absolute value less than 1. And so we know that we can actually add up all the falls. So to do that, we're going to use that formula that we just talked about. S equals a sub 1 over 1 minus r. And that is 12 over 1 minus 2/5, or 1 minus 0.4. So 12 over 0.6 is 20 feet. Now that's the distance it falls, but it also bounces back up. Every time it falls, it bounces back up that same, well, it actually bounces up and then it falls that same distance. So like over here, after the first drop, it bounces back up 2/5 of the way, and then it goes back down that same amount. Okay, and then it bounces up 2/5 of that distance, and then it falls the same amount. So you're going to have to double this, but you're not going to include the 12 because it never goes back up 12. But for all the other amounts, like 12 times 0.4 to the 1, 12 times 0.4 to the 2, all that, it does everything twice. It goes up and down the same distance on all those. So the total falls are 20, but the total rebounds are 20 minus the initial 12, the beginning drop of 12, because that doesn't get done twice. So the total distance the ball travels is going to be 28. Okay, so I'm not sure. I think maybe I changed this problem in your notes, but I'm going to do it the way the book, I don't know why I changed the problem. I was trying to animate it and it didn't work out. So anyway, this problem is straight out of your book. It's example 107.3. So a rabbit runs 2 miles in the first minute, 0.8 miles in the second minute, 0.32 miles in the next minute, and 0.4 times this distance in the next minute. Okay, so just to give you a visual of what's going on, you have this rabbit and he goes 1 mile in the first minute, or 2 miles, sorry, and then he goes 0.8 miles in the second minute, so he's multiplying by 0.4, and then he goes 0.32 miles in the next minute, and then he goes 0.8 times 0.4 to the third miles in the next minute, and so on. I couldn't get it any smaller than that. So basically you can see that he is going and going and going, but he doesn't, at a certain point, it's like he's almost not moving anymore because those distances become so tiny once that, once you've multiplied by 0.4 enough times, the distance he's moving is so tiny that he's barely moving at all. And so according to our formula for the sum of an infinite geometric series, it would be 2, which is your a sub 1, over 1 minus r, which would be 2 over 0.6, which would be 3 1/3. So no matter how long he runs, he's never going to hit that wall. If that's 3 1/3 miles, he'll get as close to the wall as can be. I mean, as long as he keeps going, he'll get closer and closer and closer to the wall, but he will never touch it.